All right. So S block elements. Where do you find S block elements in the periodic table?
Group 1, group 2.
Yes. So S block
On the
elements,
left. Yeah.
leftmost side, they are group 1 and group 2 elements. And why are they called S block elements?
Because the electron that they're supposed to, I think,
Like
their
they
valence
have
electrons
the
lies
s
in the,
orbital.
enters the is in the s orbital, outermost s orbital.
Absolutely correct. So that's the reason they're called S block elements. And these elements
Miss,
are,
can you repeat this part because both Mitali and Nishita were talking at the same time. I didn't understand one word.
sure, I will. So S block elements, they are called S block elements because their valence electron enters in the s orbital.
Miss, I can't hear you.
Hello. Yeah. So their valence electron enters the s orbital, which is why they form the S block elements. The last electron enters the outermost s orbital. So under group 1, S block elements of group 1, you've got lithium, then sodium, then potassium, then rubidium, then cesium, and then there's francium, but this is like radioactive. So we don't really know a lot about it. Like it exists only for a few nanoseconds. So it gets like really difficult to study the properties. And group 2, we've got beryllium, magnesium, calcium, then strontium, barium, and the radioactive element in this group is radium. Again, this is also both of these are radioactive. Radium, I think Marie Curie, so they had done a lot of research on this. So that is like, that's in fact, they had passed away because of radiation poisoning. They were the ones to discover this element actually, and note that, oh, like this is radioactive. Like they recorded a lot of the radioactive properties of radium. Mainly, but when we talk about the general reactions and properties and all that, we will be focusing on the non-radioactive elements. So these 5. Okay. All right. So the first thing we'll talk about is their electronic configuration. So the general electronic configuration for group 1 would be
uh
NS1.
1s2, yeah,
Yeah,
1s1.
1s2 to s. Yeah, ns1.
NS1.
Oh, sorry, not 2, 1.
1, group 1 है ना, तो एक ही इलेक्ट्रॉन जा रहा है. And for group 2, it's going to be
ns2.
NS2. Yeah, 2 electrons. Okay. And next, Acha, before we get into the properties, right? Why do we need to study about all of these elements? Like, what is the importance of these elements? A lot of these elements you guys are familiar with. Sodium, you have it in table salt. Potassium also, you get it from bananas. Magnesium, calcium, of course, like you have it in your bones. Lithium, you've got it in lithium ion batteries. So these elements are one of the most common elements that you find apart from your D block metals. And specifically, particularly sodium, potassium, magnesium, and calcium. So these 4 elements are actually very important in the human body. Not just human body, in like for life itself in general, for living organisms. Sure, yeah, we are carbon based.
Miss, your voice is breaking in the middle. Like
Yeah.
not breaking exactly. It stops and then again suddenly it starts coming.
Oh,
It is happening for me too. At first I thought it was my network.
Yeah, even I thought it was my network, but then it happened continuously 2-3 times. So I thought it might be yours.
it could be, yes. Uh, one moment, I'll switch off the video for a bit and see how it goes.
Okay, ma'am.
All right. So I was saying that these four elements are very, very important for living organisms. So sodium and potassium help in transferring um, nerve impulses. So the electricity that runs through your nerves when your brain is sending or receiving signals, um, that is controlled by sodium and potassium ions. So electricity is nothing but flow of charges. So that particular charge is provided by the presence of sodium and potassium ions. Is it better now? Was I audible?
Miss, you were audible, but I think I lost you somewhere in the middle. Can you repeat the potassium and sodium part again, please?
Sure. So sodium and potassium are are help in the human body, like in relaying nerve signals. So nerve signals are relayed through electric impulses passing through them, right? Whenever the brain is sending or receiving messages, it goes through the nerves, and flow of electricity is nothing but flow of charges. In wires, the flow of charges is through electrons, and in the human body, the flow of charges, the charge is provided by the presence of sodium and potassium ions. Ishita, yes, synapse. Synapse is the gap between two neurons. I'm talking about within the neuron itself. So when electricity travels from this neuron to this neuron, like within the neuron, right? When it is traveling, it travels in the form of the, like that passage, yeah, through the axon. The passage of that electricity is facilitated by the charge, the potential created by sodium and potassium ions. So basically, yeah, so on one side the quantity of ions increases, on the other side it decreases. That creates a potential difference, and that's how the transfer takes place, right? And magnesium and calcium also, they so they have important roles within the brain itself. Magnesium in fact is a metal that is present in chlorophyll. So now, like, it's pretty important in parts, like chlorophyll is required to make food. That is the one, like that is the place where the conversion of carbon dioxide and water to glucose takes place, right? So that's pretty important. Calcium is an important component in our bones and teeth, and even magnesium calcium ions, they help in the functioning of the heart. And also, just like how sodium and potassium help in relaying messages through the nerves, magnesium calcium also play a role in contraction and expansion of the heart, and also within your brain itself. Like I've read about how presence of magnesium enables activates or deactivates some receptors. So yeah, so these chemicals are pretty important when it comes to living organisms, which is why we have to study about them. And not just these, like lithium. Once we got to know a lot about lithium, we figured that, oh yeah, we can use them in lithium ion batteries. Cesium is like one of the most dangerous metals ever. That is because it is highly reactive, it's extremely electropositive. Similarly, strontium, barium, like the more we know about them, the more we will know how to use them, which is why we need to study about them, right? So their electronic configuration,
Miss, we lost you again.
yeah. So it's just saying, yeah, that is the reason we have to study about them, because the more we know about them, the better we'll be able to use them. That's it. Okay. The first is electronic configuration. Group 1 NS1, group 2 is NS2. So noble gas configuration NS1, noble gas configuration NS2. Next comes atomic and ionic radius. So what can you say about the trend of atomic radius in group 1?
It increases as you go down the group.
And group 2?
Same.
Same thing.
The same
The
thing.
trend is
Same
that,
thing for group 2.
yes, increases from top to bottom. And the reason? Why does it increase? Why do you think it increases?
More shells.
Yes, extra shell is added at each step. So it increases from top to bottom. What can you say about atomic versus ionic radius?
As in
So,
define them.
no. Compare atomic and ionic radius.
Oh,
Atomic is larger than ionic radius.
Yes. And
yeah,
what
an
is,
ionic radius is smaller than the parent atom.
yes. So the ionic radii for group 1 and group 2 ions, they form cations because they only have 1 or 2 electrons respectively in their shells. So their ionic radii are smaller than their atomic radii. And what is the reason for this?
When they lose an electron, the outermost shell also is lost, so the size decreases.
Absolutely. So when they lose electron, especially in group 1, they lose an entire shell. And group 2, so what about group 2? Like what if you had to
Yes, but generally, even in group 2, like for example, let's say in magnesium only, both the electrons are lost, right? When they form
Yes,
ions. So it does lose the shell at the end.
that's true. When you talk about when they form, if they have to form a stable ion, they would have to lose both the electrons. Now what about Mg plus? If you had to compare the radius of Mg plus and Mg, what can you say about that?
The radius of
Mg will
Mg
be bigger.
plus
Smaller.
should be
Smaller?
bigger. I mean, I think the
Yeah.
radius of Mg plus will be bigger.
Okay, so we have one person saying smaller, one person
No,
saying bigger.
it'll be smaller only.
Okay. Ishita, can you give me the reason why you think it will be smaller?
I mean, I'm not sure this makes sense, but then if like there are 2 electrons less, so
No, I'm talking about Mg plus, not 2 plus. So just one electron less.
1
Okay.
electron less.
Hmm. So it just makes sense to you. Mitali, why do you think it should be bigger?
Yeah. So I think it should be bigger because when you look at the structure, if you imagine the structure in front of you, when one electron is lost, according to me, the electron repulsion. Okay, no. Now that I said it, it does not make sense. I mean, it okay. So I can give you the reason of why it should decrease because if one electron is lost, the it becomes positive, right? So the electron repulsion will decrease because the nuclear charge will increase. I mean, the hold of nuclear charge for that one electron in that shell.
Yes. So how you can put it as is, as it loses an electron, the effective nuclear charge on the valence electron increases. So you can use the word attraction there. Yeah, the effective nuclear
So, ma'am,
charge.
can I say that the screening or the shielding effect has reduced because an electron is lost here?
Screening effect only applies
I mean,
to inner electrons, right? So the
okay, yeah.
number of inner
So you
electrons is
only
staying the
get
same.
the effective nuclear charge.
Yeah, so the effective nuclear charge on the valence electron increases because now there is only one electron there and more protons inside, which attracts the remaining electron towards itself, towards the nucleus, which in turn reduces the radius slightly, as compared to if there were two electrons in a regular neutral atom. So that is the reason why cation's radius generally decreases. That is the trend always across the periodic table everywhere. And
Miss, we
as,
lost you. We lost you.
okay,
After cation,
yeah,
we
so
lost.
cationic radius generally reduces across the periodic table. So generally for cations, atomic radius is greater than ionic radius, and for anions, the ionic radius is greater than the atomic radius. Doesn't matter, is it +2, +3, how much it increases will change depending on what the charge is, but as a general rule, cations के लिए ionic radius is smaller, anions के लिए ionic radius is larger compared to the neutral atom. Okay, so you can just take that as a rule. Okay, so we have checked trends individually for group 1, group 2, individually how it is compared to their atomic radius. Now, if you had to compare atomic or ionic radius between group 1 and group 2, so compare the atomic radius of
Group 1 will be bigger.
Group 1 is generally have bigger radius than group 2. Yes. So this we have already checked or studied about in the periodic table itself. Okay. All right. Radius ke baad, then we've got ionization enthalpy. What do you mean by ionization enthalpy?
The amount of energy required to remove an electron from a neutral gaseous atom.
Yes. So this is the amount of energy required to, so if we've got the nucleus over here, energy required to remove an electron from a neutral gaseous atom. So what can you say about the ionization enthalpy trend for group 1 and group 2 individually?
It should decrease down the group.
Ionization enthalpy should decrease. Okay. The same for group 1 and group 2, or is it
Yes.
different?
It should be same only.
Same.
Same, ma'am.
Yeah. And the reason why?
Because when you go down the group, the size of the atom increases. Therefore, the electron moves further away from the nucleus. Hence, ionization enthalpy decreases.
Yeah. Size increases, distance of the electron, like outermost electron, increases. So again, the effective nuclear charge decreases as the distance increases. Okay, so decreases from top to bottom. Decreases from for both group 1 and group 2. Then compare group 1 with group 2. What can you say about the ionization enthalpy values?
For group 1, I mean, there's only one electron to lose. So for them, there's only first. So for group 1, the first ionization enthalpy will be very low.
Yes.
Whereas for group 2, the first ionization enthalpy will be higher than group 1 first ionization enthalpy.
Yes. And what about ionization, the second ionization enthalpy?
The opposite.
Yes.
So IE for group 1 will be higher than IE for group 2.
Yes.
This is the second. Yeah.
Correct. And the reason for this, like, why is ionization enthalpy, why is this trend reversed when it comes to IE2?
Because it's difficult to remove an electron from already stable atom. So the group
Correct.
one when it, yeah.
Yeah. So start off by saying that so ionization enthalpy, like IE2 is the enthalpy that is required to remove the valence electron from a singly charged cation. It's the second ionization enthalpy. So on already removing one electron, group 1 elements form they attain a noble gas configuration. They have a stable octet, which is why it is much more difficult to remove the valence electron from group 1 elements, like the second valence electron from group 1 elements. But in the case of group 2, on removing the second electron, they are going to attain the stable noble gas configuration. They're going to get the octet configuration, which is why they require less energy to remove that electron. And so IE2 is lower in the case of group 2 as compared to group 1. Okay. And another point is, in general, group 1 and group 2 have one of the lowest ionization enthalpies in the entire periodic table. So in general, lowest ionization enthalpies. Okay. So that's all there is to ionization enthalpy. Then comes hydration enthalpy. This is something new. This is something we have not discussed before, but you guys must have come across this when you're doing thermodynamics. Now, what do you mean by hydration enthalpy?
Reactivity with water, or heat, no, amount of heat released when reacted with water, something like that.
No, there's no reaction involved with water. So hydration enthalpy is basically the heat energy released or absorbed. So basically, it's a change in energy that occurs when the particular species gets surrounded by water molecules. Okay, so when you dissolve table salt in water, okay, so what is table salt like? What does table salt look like when you take it just out of your box or something?
What was the question? Because I could not hear.
Oh, so I was asking, what does table salt look like when it is fresh out of the box?
Solid.
Powder, or
Crystalline.
like it's solid state, right?
Yeah.
So solid state matlab it is still in its lattice. You've got Na plus Cl minus.
Miss,
Plus.
after solid state, your voice went blank.
Yeah, so it is still in its lattice state. It's all like it's solid matlab it is still all the ions are still fixed in its lattice. Okay, now this, when you put it in put it inside water, glass of water, vessel of water, wherever, what happens to this lattice when you dissolve it in water?
The ions dissociate, right?
Yes. So ions dissociate matlab the lattice has to break, like all these bonds will have to break. So the each ion which is originally in solid state has to break free and become individual ions. Then after becoming individual ions, water is polar in nature. So if you had Na plus, the lone pair on oxygen, like the delta negative on oxygen, gets attracted to this positively charged ion. So this is what happens in the case of cations. And in the case of anions, if you had Cl minus, the delta positive on hydrogen is attracted to the chlorine. Something like this, right? So let's focus on the cation for now. So the lone pair gets attracted. So Mithali, I haven't mentioned the definition yet. I'm still explaining what happens when
Oh,
like
okay.
this thing, yeah?
Ma'am, I'm also not able to understand because again and again.
Okay. So first, initially any salt that you take is in solid state. So that means it is still fixed in its lattice, right? They're all attached to each other, rigid structure, all of that. When you dissolve them in water, the lattice breaks, like the ions, like the solid dissociates into individual ions. Then once these ions are created, they get surrounded by the water molecule because opposite charges attract. So water itself is being polar, so the negative so if you consider water as a dipole, the negative charge, the delta negative on water molecule gets attracted to the cations. All right. So immediately once each ion is free, it gets surrounded by water molecules. So the energy change that happens in the process of water molecules surrounding this. So if this particular energy change is called hydration enthalpy. So the energy change of converting Na plus gas into Na plus aqueous. So the energy change associated with this process is called hydration enthalpy. Okay, so it's the enthalpy of hydrating a particular species. Hydrating matlab attaching water molecules to it. Okay. So this depends on a
Ma'am?
lot of factors. Like, of course, how much it can be hydrated depends on the size of the molecule. So how much this also affects the mobility of the ions. So if they are less mobile, then the ions get less reactive. If they are extremely mobile, then they're extremely reactive. So hydration enthalpy does play a factor in a lot of these, how easily they dissolve. So a lot of these things. All right. So hydration enthalpy. Now, based on this, what can you say about the trend of hydration enthalpy for group 1 and group 2?
So, ma'am, could you say how hydration enthalpy differs with size?
Sure. So all the group 1 elements have the same amount of charge. So all of them form M plus 1 only. So they form singly charged cations, but the size changes, right? Lithium is small, and as you go down a group, the size of the ion the size of the ion gradually increases. So as the size increases, but the amount of charge is the same, which atom, like, uh, in which case is it easy for the water molecules to surround the ion?
The
The
last
biggest.
one. Yeah,
Why do you think it's the biggest one?
because it's
What?
big and then it can accumulate more water molecules.
But the amount of charge is the same, right? On
Huh?
But
Ma'am,
shouldn't
how
it
is the
be?
amount of charge same?
If the amount of charge would be same, then be like on any of them.
yeah.
Ma'am,
Hmm?
Ma'am, how is the amount of charge is same? The number of protons increases na as we go down.
But number of electrons is also increasing, no? So
Acha, you
ions,
are
all of them,
talking about
Valence
amount of charge upon each electron. Aisa?
no, upon the
No,
ion.
she means valence charge.
So all of them form +1 only,
Ah,
right?
okay.
Yeah. So all of them have the
Hmm.
same single positive charge only, 1 unit of charge only. So 1 unit of charge, bigger ion, 1 unit of charge, smaller ion.
But
And
isn't it easier to surround something small rather than something big?
exactly. See, this is big, which means that the outermost shell is full of electrons. And the positive charge that is contained by the proton. See, is it easier for you to surround an elephant, or is it easier for you to surround a small puppy?
Puppy.
It's like that. So the smaller the ion, the more hydrated it can become. Like better hydrated it can become. It can hold on to these water molecules more easily. Okay. So hydration enthalpy of lithium is maximum, and it decreases as you go from top to bottom in a group. And it is the same in the case of group 2 elements also. It decreases, hydration decreases as size increases. Okay. So be it group 1 or group 2, this is the logic, this is the funda, this is the trend. So hydration always decreases as charge increases. Also, okay, so this is based on the size. So we checked individually for group 1 and individually for group 2. Now, if you compare group 1 and group 2, which one do you think would be more hydrated?
Group 2. Because, no, I don't know, sorry.
What is the difference between group 1 and group 2? Like if I compare, let's say, Na plus and Mg2 plus.
Electronic configuration. It has 2 electrons in the last.
But the size also differs, right?
But
Yes,
size is very. We have a very less difference in size now.
less difference in size, compare almost like kind of comparable sizes. What else do they differ in? Like look at it. I've got Na plus here. I've got Mg2 plus here. K plus. Ca2 plus.
Their valence charges?
Yeah, the charge on them is
Oh.
different. So which one has greater charge
Okay.
on it?
Group 2.
So how do you think extent of hydration will depend on the charge?
More the charge, more the hydration.
Yeah, more the charge, the more the tendency to attract, right? Like if you have more positive charge, you can attract more negative charge things.
Okay.
So how do you compare the hydration of group 1 versus group 2?
Group 2 are more have more hydration enthalpy because they have more ionic charge.
Correct. Okay. So within each group, hydration enthalpy, because charge is the same, it only depends on the size. And if you have to compare between group 1 and group 2, group 1 and group 2 are differing based on the charge that they attain. So when we talk about hydration, we always take into consideration their cations. Okay, always take into consideration the ionic species. You would rarely ever talk about hydration of individual atoms. Okay, because even if you put the metal in water, it is going to lose those electrons, react to form the hydroxides, oxides, so eventually you're going to come to ionic state only. So always when we talk about hydration enthalpy, we talk about the ions. So charge on group 2 ions is more than charge on group 1 ions, which is why hydration enthalpy is greater in the case of group 2. So this is the reason why a lot of uh, you would see group 2 salts are more hydrated than group 1 salts. So their attraction to water molecules is so much that it, like, a lot of water molecules get stuck within the crystal structure. So you must have come across these kinds of compounds, right? If you take Epsom salt, it is MgSO4 dot I don't know, 5H2O. Earlier grade 10 may you would have come across copper salts like CuSO4 dot 5H2O,
Miss, can you explain
FeSO4
why
dot.
do they happen?
Yeah. So basically these are ionic compounds, right? So what happens is ionic compounds, you have positive and negative ions, all of them arranged in a particular lattice in a 3D, think of a Rubik's Cube kind of a thing. Now, some water molecules get stuck between these ions within this structure. Okay. So of course there's like different types of arrangements, and how these water molecules get stuck also depends on how these are arranged, whether they're arranged like a Rubik's cube or are whether they're arranged like a pyramid structure where ions are in the spaces between these other ions. But depending on all these factors, like that just decides how these get stuck. But usually they are found within the crystal structure of these ionic compounds. Okay, so that is why they are called water of crystallization, because they are found in the crystal structure. So within the rigid lattice, they are kind of like between the gaps.
Ma'am, I did not understand this.
That's okay. So this is basically about, like, you'll study about this deeper when we study about the solid state. But roughly speaking, just imagine solids have their particles that are rigidly arranged, right? They don't move at all, right? So if this was a solid state structure of one of these ionic compounds, like let's say CuSO4, so you've got like copper ions, sulfate ions, copper ions, sulfate ions alternately arranged. Then the water of crystallization is basically found in between.
Okay, so then according to the number of crystals in between, the water of crystallization is that.
Yeah. So it depends on how this crystal structure is arranged. It is not necessary that they are neatly stacked one on top of the other. It can be like
But
a
like
honeycomb.
for water, it's like a hexagon. So
Yeah, like it depends. Like it could be a honeycomb structure or it could be a pyramid kind of structure. So it depends. So that all depends on the size of these ions, which particular thing you're considering, the charge difference. There's a lot of other factors to it. Don't worry about it. But basically, water of crystallization is the water molecule stuck within the crystal structure of a particular solid.
okay.
Yeah. Okay. So yeah, because group 2 has higher hydration than group 1, a lot of group 2 salts are more hydrated as compared to your group 1 salts. And within group 1 salts, lithium salts are, they show the maximum hydration. Like for example, we have LiCl dot 2H2O. So as compared to your sodium, potassium salts, you don't see them hydrated. So your table salt, you just write it as NaCl. You don't see that NaCl is hydrated dot some H2O and all. You don't come across it. But lithium salts are hydrated. Group 2 salts, calcium, beryllium salts are extremely hydrated. And also another result from this trend is that because the hydration decreases as size increases, cesium plus ions have maximum mobility in water. Okay. So cesium plus cesium cations, they are not very much hydrated, so they are not bogged down by all the water molecules surrounding it. So imagine lithium to be like some sort of, surrounded by all the paparazzi. It's got water molecules all around it. So it's difficult for lithium ions to move around. But cesium ions, because they don't have a lot of hydration around it, they can like move around as they please. So cesium cations have maximum mobility in water. Or basically in solution state. Okay, so these are just some points. So when it comes to these properties, just remember their trends. And because of these trends, certain results. So because of the lithium and group 2 having more hydration enthalpy, like a greater negative value of hydration enthalpy, you find their salts to be more hydrated. And because cesium doesn't have, like, it has a low tendency to get hydrated, they exhibit more mobility when in solution. Matlab, they just like they can move around a lot more. Okay, clear? All right, next, coming to physical properties. So I'll just do this in a tabular form. So when we talk about physical properties, it's basically their appearance, color, shape, smell, density, boiling point, melting point. It's basically those kind of things. All right. So the first physical property we talk about is their appearance. So what do these elements look like? Sodium, potassium, group 1 and group 2.
They're soft and light metals.
They're white
Yes.
in color.
Again, they are metals, right? So they are basically grayish, silvery white. So because they are metals, they are, of course, they show luster. So kind of like a silvery white in color. And as Maya said, they are soft. So they're soft and malleable. So group 1 are so soft that they can be cut with a knife, with a butter knife, not even like a sharp knife. It is literally like cutting through butter. So group 2 also the same things. They are also silvery white with luster. Have you guys worked with magnesium in a laboratory?
We saw that burning wala experiment.
Did you get to?
Only seen, not worked.
Yeah,
Oh,
same.
I seen.
seen it. Wait, did you guys get to handle magnesium
No, this
before?
I mean,
Yeah,
in my school they said it is very dangerous, and then you all might, start just make a havoc because
Oh.
you're the mysterious that. I mean,
They did not
mysterious
trust
set
you
the
way.
guys.
entire
But
lab on
yeah, they
fire.
didn't trust us.
Okay, no, but like burning, I understand. Dangerous to play with fire and all, but you didn't get to like touch the magnesium ribbon, like bend it.
That we got
Huh.
like before that.
Right. Yeah, that I wanted to check if you guys were able to feel the magnesium ribbon. It's like really soft. You can like bend it. You can break it with hand. Yeah. So group 1 is so soft you can cut it with a knife. Group 2 is harder than group 1 elements, but in relation to other elements, like if you compare it to copper, iron, all of that other elements, they are definitely softer, but they're definitely harder than group 1. Next, density. What can you say about densities of group 1 and group 2?
They're dense.
Are
They're
they?
dense. Group 2 metals are maybe more denser than group 2. Group 2 metals are more denser than group 1, sorry.
Yes. And group 1 in general, like, are they heavier than water, lighter than water? Are they like light, or are they like other metals, pretty hard, like a block of iron?
No. They're light metals, right? So they can't be
Yes.
as dense as D block metals, but you can.
Yes. Generally, they have really low densities. And as you said, Mitali, group 2 is definitely denser than group 1. Um, and what do you say, like, what can you say about the trend of densities top to bottom?
It will increase as you go down the group.
That's what you would expect, right? And that is the general trend. If you compare lithium versus cesium, lithium to cesium, density should increase. But there's a small anomaly here that, um, specifically in the case of sodium and potassium, so potassium is lighter than sodium. This is the only anomaly. And similarly, even in group 2, if you compare roughly like the general trend, if you just compare the topmost to the bottommost, it shows that okay, there is increase in density, but the trend is not straightforward. So beryllium to calcium, it decreases, and then calcium to barium, it increases.
Ma'am, doesn't the density decrease down the group?
So that will be an
In
anomaly, right?
Yeah. So no,
like
density
for
should increase top to bottom. Why do you think it should decrease, Mayas?
because larger size.
Larger size, yes, but what is happening to the mass?
But okay, then how does the density increase?
What is density? Hmm?
Yes, ma'am.
What is density?
Then mass upon volume.
Yeah, mass upon volume, right? So density अगर increase होना चाहिए, तो two things should happen. So basically, like, it depends on both mass and volume. If volume is the same, but mass increases, then density increases. And if volume increases but mass remains the same, then what happens to density?
Density would decrease then.
Density would decrease, right? Now, if mass and volume both are increasing, then how would you decide if density is increasing or
I
decreasing?
was not able to hear you.
If mass and volume both are increasing, mass is also increasing, volume is also increasing, which is what is happening in this case, right? So lithium छोटा atom है, fewer number of protons, neutrons. Cesium बड़ा atom है. So both mass is also increasing and volume is also increasing. In that case, how would you decide if density is going to increase or decrease?
I don't know.
So then it would depend on which one is increasing more, right? Like if mass is increasing more than volume is increasing, like mass is increasing 10 times but volume is increasing only 2 times, तो फिर overall density increase होगा. And if mass is only like doubling but volume is increasing by like 10 times, then density कम होगा because volume is increasing more than mass. So that's exactly what is happening in this case. So like the trend, I mean, you can generally say based
Okay.
on their
Because
mass and size ki increase ho raha hai, but yeah, go ahead Mayas.
I thought as we go down the group, the volume increases, so the density should decrease. And in the book also they had written, so I think that is wrong.
Yeah, so density increases because volume is not the only thing, mass is also increasing. So, and check the book because maybe there definitely should be more context to it.
No, they have written large size or low density. Down the group, density decreases from lithium to CS.
That is not correct. Density increases down the group.
I corrected it, ma'am. No problem.
Okay, because that's what the numerical values also show. Sodium potassium is the only anomaly जहाँ पे even though potassium is below sodium, density of potassium is lower, because specifically in that case, the increase in size overweighs the increase in mass, like only in the case of potassium and sodium. But otherwise, numerically, you can compare the size and mass of lithium, cesium also, density should increase. And same is the case with beryllium, calcium, and calcium to barium. So wherever the size overweighs, like the increase in size overweighs the increase in mass, the density overall decreases. When increase in mass overweighs the increase in size, the overall density increases. So these trends people were able to find out based on the numerical values of densities only. Yeah. But yeah, so these specific things you need to remember, because anomalies are what are questioned a lot. They'll be like, compare the density of sodium and potassium and give reason and things like that.
What were the anomaly? In group 1, sodium is more denser than potassium.
Yeah. So even though you would expect top to bottom density to increase, sodium is denser than potassium.
And in group 2,
Repeat the reason.
Yes, Mitali?
Could you once again repeat the reason of why sodium is more potassium than
Yeah, because
why sodium?
the reason that sodium is denser than potassium is because the increase of mass, when you compare sodium to potassium, like basically it's the other way around. So increase in size overweighs the increase in mass. So if you look at the ratio, mass upon volume of potassium is lower than the mass upon volume of sodium, which means that there is more of an increase in the atomic radius than there is in the increase of the atomic mass, which is why this ratio had to be greater. Yeah. Okay, so that is about density. Now when it comes to melting point and boiling point, what can you say about the trends of melting point, boiling point?
The melting point should decrease as you go down the group, and the boiling point should increase as you go down the group.
If melting point decreases, why do you think the boiling point should increase?
Oh, I said it the wrong way. Sorry.
Yeah.
Both of them should decrease. Increase when down the group.
No, they,
because the size increases, right? So energy required.
So melting point, boiling point, basically these are the energy or temperature related to change in the phase, right? So these are more related to the intermolecular force of attraction. Okay. So if you're able to break these atoms easily from the solid to liquid state, the melting point will be lower. And liquid to gas, like if you're able to break them apart easily, then the boiling point will be lower. Okay. So lithium being small and cesium being large, the intermolecular force of attraction, and it's not just dependent on the pure atom itself, it's also depend on how the solid state is packed. Okay, so melting point and boiling point are generally low for group 1. Group 2 also is like kind of low, but like definitely greater than group 1 elements. And the trend is that they decrease from top to bottom. Okay. So reason, I mean, it cannot be simply put because it depends on the interparticle, the force between the particles. It also depends on how they are packed in the crystal structure. So all of these things it depends on. Okay. So they're generally low. So within the whole of periodic table, along with mercury is like liquid at room temperature. Gallium is another liquidy metal, like you just put it in the hand and it melts. Cesium is also one of the low melting metals. So you just hold it in your hand, or you just like rub it in your hand, like give it a little bit of friction, and it turns into liquid state. Okay. So it's generally low, it decreases from top to bottom. When it comes to group 2 elements, the trend is not very regular. Like for example, magnesium, which is like somewhere in the middle, has the lowest melting and boiling points.
Why so? Like, why is it regular?
So again, I told you, right? Because it depends on many different factors. So it
Yeah.
depends on how they are packed, the intermolecular forces.
Okay.
Yeah. So in some cases, one factor outweighs the other, which skews.
So there will be.
Yeah.
Okay.
Yeah.
Got it.
But it is definitely greater than group 1.
They won't ask why.
No, they won't
But
ask like why it is not regular, because you guys
we don't
haven't
need to learn
studied structures.
the pattern, na?
No, you don't have to. Just know the extreme it is, like magnesium has the lowest. Um, that too, that's also pretty far off, but just because, yeah, it is the lowest, that's why. Okay. Next comes flame coloration. So, have you guys done practicals this year?
Not this year, but then we did flame coloration last year as well.
Oh, you guys did it. Okay.
Yeah.
So generally, like if you'd had normal school and if you had to do practicals, this year you would have had salt analysis. So salt
Oh,
analysis, matlab, you would have to identify the cation and anion in a given salt, like mostly cations, but yeah. And flame coloration is one of the important aspects of identifying which ion it is. Yeah. So, flame coloration, matlab, as the term suggests, it is literally when you burn a particular metal or a metal salt, what color the flame turns into. So that completely depends on what metal is there in the salt. Normally, like sometimes it depends on both cation and anion, but mostly what cation is there in the salt. So it's basically one of the characteristic tests for metals. And it is like so characteristic that the flame coloration or the color of the salt, especially when it comes to D block, right? You can figure out if, especially when you have variable valencies, whether the particular salt has a +2 ion or a +3 ion. Like iron, for example, that's the best example. Fe2 plus has like a greenish color, and Fe3 plus ions usually has like a reddish color. So flame coloration is really important when it comes to identifying the ion itself. Now, why does flame coloration happen? Like, why do metals give out a characteristic color when it comes to, like, when they're burning in?
Related to the atomic spectrum thing, right?
Yeah, correct. Yes, Mitali. So it's the exact same reason or the phenomenon that happens in the spectrum. So atoms, so when you're burning a particular atom or like a metal, right, you're literally putting it in the middle of an energy ball. So when you expose energy to a metal, then of course the electrons are going to jump around. They're going to go to a higher level and then jump back, which when they jump back, they emit that particular wavelength of energy, which gives the color of the particular flame. That's basically what happens there. Okay, so coming to group one, um, lithium. Do any of you remember, if you have already done flame test, what color this particular metal imparts?
Red.
So lithium has like a dark red or crimson color, maroonish, dark red. Sodium, this flame coloration, every one of you have seen. Even when you don't know that that's what you're seeing, you would have seen it.
Yellow.
Yeah. So some of the street lamps that are yellow, right?
Wait, they have sodium in them.
Yeah. So sodium lamps are like one of the commonly used lamps. So you've got like neon lights, which are used in advertising and all of that stuff. Apart from that, you have mercury lamps, you have sodium lamps. So sodium lamps have this characteristic like yellow light that they give out. Potassium. So potassium gives out a violet light, violet coloration. Rubidium. So
Rubidium?
rubidium,
Orange or no? Yeah. It's
so
also purple-ish, right? I
yeah,
don't.
so that's also like a purplish color. In your book, it's given red violet. So basically, it is like violet but more on the redder side. So purple is like a mix of red and
Okay.
blue, right? So if you skew more towards the red side of it, yeah. And cesium gives out a blue flame.
No.
Now coming to group 2 elements, I've got beryllium, magnesium, calcium, strontium, and barium. So beryllium,
No.
no, this doesn't give out any color. Magnesium,
Again, no color flame.
yeah, there's no particular color to it. Calcium,
Brick red.
red, yes. Strontium, The strontium is a darker red than this, so this is crimson again. And barium gives
Apple.
apple green. Yeah. Okay. So how come beryllium and magnesium don't give out any color? Does it mean that they don't burn? But you've seen magnesium burns with a really bright white flame, right?
So question to the teacher, and she said that magnesium and beryllium, both of them burn,
Mm-hmm.
and they give out their light. It is spectrum. It is a
Correct.
spectrum. Hence, you will only like
Yes.
white color or like the same color. So that does not make a difference.
Exactly. So the key point here is that they do follow the same phenomenon, but whatever wavelengths are emitted, they are not in the visible spectrum. So they're literally not visible to you, but they give out light. Yeah. So they emit rays in, I think, UV. It is like much brighter than visible, like much stronger than visible. So yeah, that's why they're not visible to you. That's why they don't have like particular color as such. That's why magnesium, when it burns, you need to protect your eyes. Like you can't directly look at the flame. It is extremely bright because it gives out a lot of energy, and that is the reason you kind of, like the flame also looks white. That's why it's always described as dazzling white flame, is that it gives out a lot of energy. Okay? So that's the main point. It's not that they don't give out any color, just that they are not in the visible spectrum. So you don't associate them with like specific colors as such. Okay. Another key point when it comes to flame coloration is that, so the whole funda with flame coloration is that you expose metal to energy and electrons are excited. Now just take this some steps forward and you get photoelectric effect. So you give them enough energy and it is enough to excite them beyond their atoms. So you give out energy and the electrons gets ejected. So that particular property is like, because of that particular property, so potassium and cesium are used as electrodes in photoelectric cells. Okay. So because their electrons get easily excited on exposing them to energy, they're used in photoelectric cells. All right. So you guys wanna see what these flame coloration tests look like?
Like the process of how they're carried out.
Yeah.
If you show us practically, then yes, videos तो you only can see. I want to do it practically.
Sorry, practical घर पे तो नहीं कर सकते ना? It's too dangerous, and also I can't get the metals inside the house. Like handling will be difficult.
Yes,
So
I was just kidding. Even I
mhm,
know you can't do it at home.
yeah.
Yeah,
So
but I'd like to see them.
yeah. So like, do you want to see them right now in the middle of class, or would you prefer if I sent the videos after the class? Hmm? Come on, guys. Would you prefer if you saw them now, or do you want, or we'll do both, right? Like I'll play them right now, and you can
Ma'am, can
also
you
see
show me?
them.
Yeah.
Yeah,
Miss, can you show them now?
yeah. Okay. Let me do full screen. Okay, there you go. So this is lithium. You have a reddish flame. Sodium, this is the yellow color. It's like the yellowest yellow. So potassium burns with a purple flame. And this is rubidium, which is again red violet. And cesium burns with a blue flame. Like this is like proper blue. Okay, so these are the colors. So Ishita is asking why stuff ka flame is blue. Who wants to answer the question? Why do you think stuff ka flame is blue? Like what burns in stuff ka flame?
I am not sure, but like it can't be cesium, right?
No,
I
because
mean,
cesium, no, definitely not possible. Guys, stove में क्या होता है? Like gas connection में, like what gas do you get in your gas connection?
normal gas, LPG.
LPG का
What?
full form
Yeah.
liquid petroleum gas. So it's basically your petroleum gases, butane or isobutyl. I'm not sure, but it's definitely one of the hydrocarbons. Natural gas है वो. Saturated hydrocarbon है, that's why it burns with a blue flame. So unsaturated, like in your candle, works with a sooty flame. Now there you go, both group one. No one's one and two. Okay, alkaline earth metals.
Certain alkaline earth metals are used in firework display and produce colorful, vibrant lights when ignited. On a smaller scale, the Flame Test Lab allows a visual representation of the characteristic flame colors these metals emit. The three metals we will use in our flame test are calcium, strontium, and barium. The materials that we will use for the flame tests are the flame test chemical solutions, 3 200 milliliter beakers, wooden sticks for soaking into the
I'll just
solutions,
forward through this.
a Bunsen burner, and a flint lighter. To prepare for the flame test, we soak the wooden sticks in the chemical solutions for about an hour so that the metal ions absorb into the wooden sticks. Before we go into
There you go.
As you can see, the first
So this
metal
is
that we
strontium.
perform in the flame test sample is strontium, which emits a vibrant red color. All the colors
So
that
like
the
a really
metals
deep
emit in the
red
flame test
color.
are part of the visible light portion of the electromagnetic spectrum. Wavelengths in the visible light portion are within 400 to 800 nanometers. The red color that the strontium emits has a wavelength between 620 and 780 nanometers.
So this is strontium with its
the next
red.
metal that we will perform the flame test
Calcium.
on is calcium. Calcium emits an orange colored flame. The orange
So
ions produce
this
more
is
of
a
wavelength of
lighter
500
red color as compared to
7
strontium.
nanometers. The last metal is barium.
And
Although the
barium
color of
burns
the
with a
flame is
green.
hard to see, barium emits a green colored light.
It's difficult to
Green
see.
has a
Very
wavelength
nice if
of
they'd done it in the
400
dark, but
to
yeah,
570 nanometers.
it has a greenish
Although
color.
we did not test magnesium, which is another alkaline earth metal, this metal produces a white colored flame. Here we decided to experiment by combining metals in the flame test. This is a combination of calcium and strontium,
which is a mix between orange and red. The other combinations that we tried were not very successful because barium did not produce a strong green color.
There you go. So yeah, lots of flame tests. Like in this other video, they were doing copper. If you're curious about it, you can explore more. But yeah,
Copper is also blue, right?
copper again, it depends on Cu plus, Cu2 plus.
Okay.
Also, like the flame test will not reflect the color of the salts. So color of the salts it again depends on uh, how many electrons are in the d orbital for that ion and everything. Flame test is like to what extent they're getting excited and then de-excited and what wavelengths they emit. So it may not always match.
So some of it is ready for a trim. It looks like September's just around the corner, so it's time for our next education in chemistry. And this month we're going to be visiting a demonstration that has caused some life-changing injuries in the US and has even had some calls for it to be banned. But there's absolutely no reason for this demonstration to be banned as long
There you go. Are you guys able to see this in full screen?
Yes, ma'am.
Oh. So this is lithium. That's sodium. So same thing, flame test. So they've got the metal compounds in the beaker and he's lit them up. This is boron, this is copper. It's a mix of different potassium with its violet flame. So they just selected elements so they get the rainbow color. So starting from violet to red.
Now, before you go,
Yeah.
The main risk associated with
So yeah. So those are like the characteristic colors of the flames. I'll show you what sodium lamps also look like. There you go. So the yellow color street light. I'm not sure if now they're using LEDs, it might have changed, but yeah. So back in 80s, 90s, I think even in early 2000s, these particular kind of yellow street lighting you see are from sodium lamps. So yeah, you would have seen flame test of sodium, even if you didn't realize it was sodium's characteristic. Okay. All right. So that's the flame test. So in organic chemistry is always fun doing the practicals with this than, like the theory part of it. Yeah. So that's it for the physical properties. Now talking about chemical properties. Ishta asking, traffic lights are just colored, right? Yeah, I think traffic lights, they just, they may be using colored LEDs. They're definitely not using these kind of chemicals for sure, because it depends on like what bulbs. Yeah, the solar driven LED lights. Earlier, I've seen some cases where traffic lights, they're just colored, they're just covered with a color glass also, with a regular white light. Now, once LED has come into this thing, they've started using LED lights. All right, So chemical properties, as usual, just like in organic, what you've seen here also, it's just reactions with different things. So the first thing, the substance that's all around us, how do group 1 and group 2 react with air? So do you think group 1 and group 2 react with air?
Yes, ma'am, they do.
Yeah, they do. They are extremely reactive, they are extremely electropositive. So they do react with air, and which is why they lose their luster. So there's like a white coating on it, will become dull because they react with air and they form like a layer of
They
oxide.
darken, right? They darken, right?
They darken, yes. So they become dull, they lose their shininess. This is due to formation of the oxide. This is in fact the case with a lot of metals. Same thing happens with aluminium, iron, copper, and all. Of course, they show rusting. But yeah, group 1, exclusively the formation of oxide, they become dull. This oxide, if there is moisture in the air, so if it is humid like we have in India, so the oxide can get converted to hydroxides and carbonates. So you have a metal, you have a layer of the oxide, it reacts with H2O, then it forms hydroxides, reacts with carbon dioxide, then it can form carbonates. Okay. And because of this reason, they are stored in kerosene. So all of this we are talking about group 1 metals, huh? So group 2 is not as reactive as group 1. They don't need to be stored under kerosene and all that. Okay. So they do become dull. This happens with group 2, but all of like it's not violent, it's not extremely reactive. Okay. So now coming to the actual, like this is what you can see what actually is happening. Okay, so if you want to make it react in air, so increase the temperature. So this is what is happening on its own passively if you let it be. Now if you want to create the actual reaction, then so on burning in air, group 1 forms oxides. So oxides are your regular oxygen atom. Peroxides are O2 2 minus, and superoxides, so O2 minus. So these like group 1 forms all 3 compounds. So group 2 does not form peroxides and superoxides, they only form oxides and nitrides. Okay. So these are oxides, they are peroxides, and they are superoxides. Now, because you're burning them in air, lots of oxygen available. So each metal is going to form the compound that it is stable with. So it like the particular anion that it is stable with, so that particular anion is formed. And which one of these is formed, whether a particular atom prefers oxides or peroxides or superoxides, depends on the size. Okay, so we have lithium, sodium. So lithium is capable of forming only oxides. It forms oxides and nitrides. Sodium forms peroxides. But the bigger atoms, right? So potassium, rubidium, and cesium, these 3 form superoxides.
What do group 2 form? Oxides and
N3
nitride.
minus, nitride, yes.
And what were the previous points for group 2? They lose luster and formation of oxide, and the second point.
That's it. So like if you leave group 2 elements out, they lose their luster. There's like a coating of their oxide on it. And that's it. Like they don't have the tendency to form like oxides, carbonates. They don't need to be stored in kerosene and all. They're not as reactive as group 1.
Okay.
Now this depends on the size. So basically, again, these are salts, these are ionic compounds, right? So stability of ionic compounds and whether an ionic compound will form or not depends on one, formation of ions, and two, the lattice enthalpy. So lattice enthalpy matlab the stability of the lattice structure. So bigger ions form stabler structure with bigger anions, which is why the bigger cations prefer getting converted into their superoxides. The smaller ones are happy with, so that's the reason it goes in this particular order, right? So lithium forms like really small, it takes after the smaller ones, forms M2O like oxides and nitrides. Sodium forms peroxides, and the bigger ones form superoxides. Okay. Another more properties of their oxides. Okay, we'll go over general reactions of group 1, group 2, and then बाद में we'll go deeper into properties of oxides, properties of hydroxides, properties of halides, and all that. Now, when it comes to group 2, so beryllium and magnesium, on burning in there, they react with oxygen, forming their oxides, as well as nitrates. So they react with both oxygen and nitrogen in the air. But the bigger ones, so we have calcium, strontium, and barium. So they form only oxides. MO. Okay. So this is reaction with oxygen. Now when it comes to water, so this is reaction with air. So air may mostly oxygen is more reactive, but in certain conditions like lithium, beryllium, and magnesium also burn with nitrogen. Otherwise, rest of the elements all react only with the oxygen. Next, when it comes to water, again, metal plus water, this you guys are familiar with. What do metal and water react to form?
Metal hydroxide and hydrogen gas.
Absolutely. So they react to form
Hello.
hydroxides. Yeah. So they react to form hydroxides and they displace hydrogen gas from water. So this is the case with both group 1 and group 2. Group 2 may again because of the reactivities, the tendency to react with water changes, but the form of the reaction remains the same. If at all they react with water, they form hydroxides and release hydrogen gas. Okay. So group 1, all of them are capable of reacting with water. So right from lithium, sodium, potassium, rubidium, and cesium. So all of them displace H2 from water. And it's not just water. They are capable of displacing H2 from any protonic substance. Protonic substance matlab any substance that is capable of giving a proton, H plus ion. So that involves, apart from water, you have acids, they displace hydrogen from acids. even weakly acidic substances like ethine, right? So they are capable of displacing this particular hydrogen from ethine. And even ammonia. So even though ammonia generally is basic because of the lone pair on nitrogen, these metals are so electropositive and so reactive that they are capable of releasing the hydrogen from ammonia. Okay, and yeah, but coming back to water, specifically with water, they form hydroxides, which are, of course, basic in nature. Now, coming to group 2 elements, so beryllium, magnesium, calcium, strontium, barium. So, beryllium does not react with water. Magnesium only reacts with hot water. With cold water, it doesn't react, but these three are capable of reacting with cold water also. The reaction remains the same, just that the tendency to react is different. So the bigger ions, the bigger atoms are more reactive, so they are capable of reacting with cold water. Magnesium is not as reactive, so you need to push it a little. So you increase the temperature, hot water ke saath it reacts. Beryllium is not at all reactive with water. It does not react with cold water or hot water. But yeah, but whatever reaction they undergo, magnesium se leke barium tak, this is the same reaction they undergo. They displace hydrogen from water and form basic hydroxides. Yes, Mitali, you were able to ask something?
No, ma'am, that was by mistake.
Okay. All right. Next comes reaction with hydrogen. The reaction is again the same. With hydrogen, it is not an easy or a spontaneous reaction. So group 1 elements react with hydrogen at 673 Kelvin. You need to increase the temperature to almost like 300 degrees Celsius. With the exception of lithium, which will react with it at 1073 Kelvin. Extremely high temperature. So metal plus hydrogen, they form metal hydrides. So hydrogen takes the anionic position here, so they form metal hydrides. So metal hydrides are ionic solids and they are extremely high melting solids. And this is because of intercoulombic forces. Yeah. And nothing special as such. Now, but when it comes to group 2, so they don't react directly with hydrogen, like hydrogen gas ke saath the reaction is not that easy. Again, the metals react with hydrogen gas at a high temperature on heating, but beryllium specifically doesn't react with hydrogen gas directly. So again, beryllium not being very reactive, it requires a little bit of catalyst. So it takes hydrogen from other sources. The most common source of hydrogen being lithium aluminium hydride, LiAlH4, in the presence of beryllium chloride. That is the only way this is going to form beryllium hydride while giving out lithium chloride and aluminium chloride. But all the other group 2, right? So they react with hydrogen with heat, forming hydrides. Okay. And these hydrides, on dissolving in water, they form metal hydroxides. So the only exception in reaction with hydrogen is beryllium. Group 1 and group 2 both react. Of course, you need to provide heat to it. They react at really high temperatures, forming metal hydrides. In the case of group 1, metal hydrides are high melting solids, ionic compounds. In the case of coming to beryllium, it does not react with hydrogen gas, but it forms hydride by taking hydrogen from other sources, which is basically lithium aluminium hydride, LiLH4. If you remember, organic compounds may be whenever you needed reduction to happen, right? Whenever you needed to add hydrogen. Actually, oh, you guys have not come across this. So basically, when we wanted to reduce aldehydes or ketones to alcohols, lithium aluminium hydride was one of the preferred methods to do it. So whenever you want to provide hydrogen in a reaction, this is like a pretty common reagent that is used. Next comes reaction with halides, halogens. So reaction with halogens when it comes to group 1. So group 1 and group 2 elements excluding beryllium. So group 1 and group 2 excluding beryllium, they form, like, they undergo a similar set of reactions. Okay. So
I can't see the bottom part of the page.
oh, how about now?
Like I can, now I can.
Okay. All right. So group 1 and group 2 excluding beryllium, they form, like, they follow a similar, so they follow similar reactions, similar kind of reactions. Both of them form metal halides. So group 1 halides are in the form of Mx, group 2 is in the form of Mx2 because of their valencies. Both of them are ionic compound, like all of them are ionic compounds. So they are ionic compounds. But the special thing is that, again, when it, like, depending on the size, so lithium halide shows a lot of covalent properties. So lithium halides are somewhat covalent. Why do you think lithium halides are covalent? Like, what is the reason for this?
Lithium is it's very small in size, and besides that, it has very high polarizing power.
Exactly, correct. So lithium has a high polarizability due to its tiny size. Which is why it, so polarizability matlab the ability to distort the electron cloud. So you've got your cation and you've got your anion with its negative charge. So when an ion is small, its nucleus is closer to this electron cloud. So this is going to exert an attractive force on the negatively charged anion and distorts its electron cloud a little. So now it is no longer a clean separate cation and anion. So this starts showing like a small amount of covalent bond properties, like electrons look like they're being shared between both the ions. So that is where your covalent nature comes up in ionic compounds. So the larger ions don't show this, so smaller ions and ions with a high charge that show this. So yeah, So lithium ions, like they show high polarizability. They're highly polarizing due to their small size, which is why lithium halides show some amount of covalent properties. So the polarizing property, right? Polarizability in the case of cations, it is high when the cations are small, and it is high when the anions are large. Because large anions matlab the nucleus doesn't have a hold over the electron cloud, which is why the electrons can move easily. So due to these two factors, lithium iodide. So lithium iodide is the most covalent compound out of all the metal halides. So maximum covalency is shown by lithium iodide because of small size of lithium and large size of iodine. Now again, group 2, with halides, they form ionic compounds of the form MX2. They're also like ionic compounds, so like high boiling, high melting, all of those things soluble in water. Now beryllium is an exception, right? So what does beryllium do? So beryllium only forms beryllium fluoride and beryllium halide, again just like with hydrides, under special conditions. It does not react directly with the halogens, but it takes the halogens from other sources. So in the case of fluoride, so you take beryllium oxide in the presence of ammonia, make it react with hydrogen fluoride, HF. So this gives a complex with ammonium fluorate, which on heating, you lose ammonium fluoride, giving you BeF2. Okay. So if you want beryllium halide, this is one way to prepare it. So ammonia is required to form this ammonium complex. Now this is like a large complex. You've got beryllium in middle connected to 2 ammonium ions and 4 of these fluoride ions. So on heating, beryllium fluoride separates out from ammonium fluoride. Now to prepare beryllium chloride, again take beryllium oxide. So 2 ways of preparing beryllium chloride. So either use coke, make it react with chlorine gas, or make it react with carbon tetrachloride. So both these reactions, so one takes at a higher temperature. This one takes at 873 Kelvin. This one takes place at 973 Kelvin. Both of them give you beryllium chloride and carbon monoxide gas. Okay. Again, a roundabout way of preparing beryllium halides. So all the other metals, they directly react with chlorine, all the halogens basically to form their halides. But if you want beryllium halides, you need to go about a roundabout way. That too, you can only prepare the chlorides and the fluorides, the more reactive elements out of the halogens. Fluoride you can prepare by creating the ammonium complex, and chlorides prepare it with the help of carbon. So either use carbon tetrachloride or a mixture of carbon and chlorine gas. Okay. And then we have reducing nature. So in terms of electrons, how do you define oxidation and reduction?
Gain of electrons is reduction and loss of electrons is oxidation.
Loss is oxidation, gain is reduction. So if group 1 and group 2 elements are electropositive, are they good? Would you say they are good reducing agents or good oxidizing agents?
They're good reducing agents.
Yeah. So group 1 and group 2 have a tendency to lose electrons, which means that they're providing electrons for the other substance to take up. So they're helping in reducing the other substance. They themselves are getting easily oxidized. Okay. Now, what is the trend of reducing nature within? So let's take up group 1 and group 2 separately. So within group 1, what is the trend of reducing nature?
It increases down the group.
So Li2CS reducing nature should increase, right? Which means that which is the best reducing agent of out of all the group 1 elements?
Lithium, ma'am.
But reducing nature increases
What
as
was the
you go to
question? What was the question?
So the trend of reducing nature should increase as you go from top to bottom in the group. So I asked, which is the best reducing agent out of group 1 elements?
Ma'am, but shouldn't it be the other way?
Cesium.
Think
Shouldn't
about
it
it.
decrease as you go down the group?
Why do you think it should decrease, Mitali?
Okay, so reducing nature is where what do you say? An element gains electrons, right?
Yeah. Yeah.
I don't know. I'm
No.
lost.
So reducing nature. So basically, think of oil rig.
Yeah, that's exactly what I thought about.
So reduction is when an element gains electrons.
Gains electrons, yeah.
Reducing nature matlab we are talking about which is a good reducing agent. So if like let's say I want to reduce copper. So Cu2 plus, say if I want to reduce it to Cu, I need something to give me electrons, like I need something to give Cu electrons so that this can be reduced. So when we're talking about reducing nature of group 1 elements, which of these elements is the best reducing agent? Which one can give away electrons easily? Or where does it take the minimum effort to give away electrons?
Oh, okay. So in that way, cesium, because the electron is far away from the nucleus and it's easily lost.
Yeah, you would expect that, right? So generally, but in group 1, lithium is the best reducing agent. So this has this. So lithium is the strongest reducing agent, followed by cesium. So from sodium to cesium, the trend is as you would expect. Cesium is strong, followed by rubidium, followed by potassium, followed by sodium. But lithium alone is an anomaly there. It is the strongest reducing agent. Okay, followed by cesium, followed by rubidium. The rest of it is just as how you would expect it. Only lithium, and that leaves sodium with the lowest least reducing out of all. Yeah. So the reason is that reducing nature, so generally whenever you're doing oxidation reduction reactions, right, you guys have studied redox reactions, right? So do you know what is the standard electrode potential and all that?
Yes, ma'am. But could you once just go over the definition if it's okay?
Yeah, sure. So basically, generally reducing nature matlab it's always in comparison of one element with the other, right? So if you take a zinc and copper couple, then depending on the reactivities of zinc and copper, the one which is more reactive will reduce the one which is less reactive. One will have a tendency to give electrons more than the other, so it's going to overpower the other one. Itself will get oxidized, the other one will get reduced. Right? Similarly, if you take copper and silver, copper is more reactive, so this is going to be like, I am going to give electrons, so silver is going to get reduced. So reducing nature, you can always figure it out only in comparison with another element. So in order to standardize it, like obviously take any pair. So if you take zinc copper, copper is not reducing at all. But if you take copper silver, copper is reducing in this case. So to avoid these complications and confusions, reducing agents are like the reducing nature, the tendency is all taken in reference with hydrogen. So compare any metal with hydrogen. If it is easier for that metal to give away electrons, then it is a stronger reducing agent. And this is quantitatively measured. Now, because we are talking about transfer of electrons here, it is quantitatively measured by checking what is the potential difference that is created between a standard hydrogen electrode and the metal electrode. So these values are called the E0 values. The standard potential difference that is created when a metal electrode is connected against a standard hydrogen electrode. So yeah, so this is the quantitative way of measuring this thing. Now when it comes to measuring against hydrogen electrode, and you're going to take electrolyte to create the couples. So this particular electrode potential, how high or low it is, it depends on three things. So when you dip an electrode, first the metal solid needs to be separated from the electrode itself and become an individual atom. Then the individual atom should lose electrons to become an ion. And then the ion gets hydrated, like it should go within the solution. So M plus gas in water should get converted to M plus aqueous. Okay. So the energy change associated with this is sublimation enthalpy. The energy change associated with this is ionization. And the energy change associated with this is hydration enthalpy. Now, comparing the elements of group 1, right? Ionization enthalpy, if you take only this into consideration, then of course, lithium is weak, like cesium is definitely stronger, or even sodium is stronger than lithium in the case of ionization enthalpy. Same in the case of sublimation enthalpy, although I imagine it is almost comparable. But yeah, just taking only both of these into consideration, lithium is weaker than the other elements. But we have seen that lithium, because of its small size, it has a very high tendency to get hydrated. It is like one of the most stable cations in aqueous solutions. It's got an extremely high hydration enthalpy. So because of this single step, this basically compensates for the other two processes that are happening, that are taking place, which is why the standard electrode potential of lithium is greater than the standard electrode potentials of all the other elements, which is why lithium happens to be the strongest reducing agent. So if the E naught value is highly negative, so E naught, if it is two things, okay, if E naught value by default is negative, it means that it is easily reducing. It is harder to get oxidized as compared to hydrogen. So it will have a reducing tendency. And higher the negative value, the more easily it's going to reduce other substances. Okay. So for a good reducing agent, for a strong reducing agent, you want the value of E naught to be, the magnitude to be as high as possible, and the sign should be negative. So you need a high negative value of E naught. And E naught depends on these three things. Like this is what happens during reduction process. So electrode से solution के अंदर जाने के लिए first the individual atom needs to separate out of the solid electrode. So there is sublimation involved. Then the neutral gaseous atom should lose electron, which depends on ionization enthalpy, and the atom should be dispersed in the solution, so which involves hydration enthalpy. Now, because the hydration enthalpy of lithium is so high, that is the only factor that just like shoots it.
Liz, I lost you after hydration.
Yeah. So step 1, sublimation. Step 2, ionization. Step 3, it needs to get dispersed in the solution, which involves hydration enthalpy. Now, because lithium has an extremely high negative hydration enthalpy, that overweighs these other two factors, which makes it the strongest reducing agent. So it's because of its small size, it has extremely high hydration, which is the only factor for it to be the strongest reducing agent that it is. So it has an extremely highly negative E naught value. Okay.
Yes, ma'am, got it.
Okay, cool. So this is in group 1. So that makes sodium the least strongest this thing. So the tendency, like the trend in the group is to increase. This definitely is followed. Only lithium is an anomaly because of its hydration enthalpy. Otherwise, rest of the elements, it increases as you go from top to bottom in the group. Now, when it comes to group 2, their values also, generally their E naught values are highly negative. The trend increases down the group. But obviously, just like with the reactivity, they are weaker reducing agents than group 1. ठीक है. So this is the trend with the reducing nature. Reducing nature, group 1 and group 2 are very good reducing agents. Within the groups itself, the general trend is to increase from top to bottom. But lithium is an anomaly. It is the strongest reducing agent because of its high hydration enthalpy. if it's like for 1 mark, 2 mark, you can just say because of high hydration enthalpy. Just for 1 mark, you can say that. But if you get this for 2 or 3 marks, then elaborate on the whole process. Ki reduction में क्या होता है, like E naught value depends on the standard electrode potential, depends on all these 3 individual enthalpies, all these 3 processes. So yeah, it like sublimation ionization may be high for sodium, potassium and all of that, but hydration enthalpy is so high for lithium that it is enough to overtake other factors. Okay, all right, so it is 5 o'clock. We're done with like half the
How
chapter.
do we write the answer like completely?
So
If they ask why lithium is the strongest, like can I try and if that's right?
yeah, go ahead.
Lithium is the strongest reducing agent because it's E naught. It has a high E naught value,
Yeah,
which is because of because of a hydration enthalpy, and this is just for 2 marks. If
1 mark.
acha.
But
And
ma'am,
what do
Because
I
it's
write
a
if it is
single
for 3 or
statement.
something?
If it's for more than that, if it's 2 or 3, then elaborate on it. So your first statement is the same because it has a highly negative E naught value. Then elaborate. So E naught value depends on the following factors. Give this reaction, say sublimation enthalpy, this reaction, say ionization enthalpy, and this reaction, say hydration enthalpy. So E naught is the sum of all these 3 enthalpies. And yeah, like some of it. Okay, so telling if you have to write it in an answer. So E naught is depends on the sum of all these 3 enthalpies. In the case of lithium, the hydration enthalpy is uh, high enough that it overweighs the sublimation and ionization enthalpies, which results in the highly negative value of E naught. Correct?
Yes.
That's it. You just have to describe what happens here and mention in lithium it is high enough to overweigh the other two. Cool. So this leaves us with just properties of specific compounds. So we have oxides, hydroxides, halides, and then all these sodium like sodium carbonate, calcium carbonate, all of these other things. So all right, so we'll finish it up in the next class. Okay.
Ma'am, so that's all you will do in the next class? Because I might not attend the next class because I have a housewarming to attend. So you'll still record it and put it on YouTube.
Yes, it will be recorded. I'll put it up and we'll finish off the S block